All right, we are again on the Break It track for Shmoocon 2008. The next talk that we have is 21st Century Shellcode for Solaris by Tim Vidas.
Thanks. I'd also like to thank everybody for waking up early and attending the noon talk. Appreciate you dragging yourselves out of bed and coming down here to the Break It talk. So like it says, 21st Century Shellcode for Solaris. It hasn't really been revisited for a few years, so I thought we'd take another look at it. I kind of pulled out of a pet project where I was supposed to go do something, and then I kind of did it in a way that wasn't supposed to be able to be done. So I decided to talk about it. All right, so who am I? What really matters is you probably don't really care. You're already in the room, so you got here. The description was good enough to get you here. I had 50 slides. We have 50 minutes. You do the math. We don't have time to dick around with who people are and who knows who and that kind of stuff. So normally I like inline questions, but again, 50 slides, 50 minutes. If you have a question that's more for you, kind of hold it off. I'll be around the rest of the weekend. You can find me. I've got red hair, pretty easy to find. I'm a tall guy. If you have a question that's more for everybody in the room, go ahead and raise your hand or throw something at me. I can't really see very well with the light, so just take out one of the shmoo balls, throw it at me, and we can see if we can answer it right there. All right. So what are we going to do? Here's the obligatory what we're doing slide. We have shellcode background. How many people know of shellcode, the word shellcode? All right. How many people have programmed in assembly at some point in their lives? How many people have written actual shellcode? How many have written shellcode and submitted it to some project like Metasploit and it's actually being used somewhere? Okay, so okay, good. So I get a demographic where we go. Maybe we can go through some of these preliminary slides a little bit faster. So we'll do a little bit of some do-it-yourself, how you can do shellcode, how you can play at home. Look at some Solarisisms, and then finally we'll get to the newer, smaller shellcode payloads. Look at the thought process and do some demos. All right. So errata for this slide deck. A few assumptions. Intel 32-bit architecture. We're using Intel syntax on the slides. If you're an AT&T guy, you have to do the transposition and the adding of characters in your head. And yeah. Nope, no Spark. x86. So all the code you need to play with is going to be found throughout the presentation. So when you go to the website after the con and you download it, you should be able to do the cut and paste thing out of Acrobat and get it to all work. No zips or going to weird websites to find files and stuff like that. All right, so what is it? Most of you guys have seen it. Historically, it's something that gives you a shell, like bin.sh. But anymore, it's practically just very low-level architecture-dependent stuff that does some action now. So we have all these different actions that like Metasploit has built into it now. So shellcode's not new. If you think shellcode's new, you really need to think about LSD. All right. Back in 2001, last stage of Delirium put out a pretty comprehensive guide to Unix-style shellcode. It's the Unix assembly code development for vulnerabilities illustration purposes. Just Google it. I don't think they actually maintain an actual site anymore, but I need to point this or something. Hate all this AV stuff. How about that? Is that better? Okay. So anyway, I don't know if they still maintain a site, but if you do the Google research and you search for that string, you'll find the paper somewhere hosted. All right. So why you must not depend solely on Metasploit. So maybe you need to do something custom, right? Metasploit has all these built-in payloads, and that's fine and dandy, but maybe they don't have the exact one that you need. All right, detection avoidance. We have IDSs, we have antivirus, we have firewalls. Almost all of those are still signature-based. So if we have a payload that fits a pretty specific signature, and everybody's using Metasploit, then you're going to get caught just like everybody else is going to get caught. So if you can write your own code, you can write variants that accomplish the same tasks, but get past the signatures. All right, practice, right? Everybody needs to know what this stuff is doing at the low level. This goes hand in hand with the last bullet. Do you really know what that Metasploit binary blob does? right? Everybody can click the buttons and get MSF payload to generate some stuff, but do you really know what's going on behind the scenes? And then the middle two slides, the discovering new methods and the creating the smaller payloads, that's kind of the crux of what we're going to get into when we get into the Solaris stuff later on in the slide deck. All right, Shellcode 101, how to play at home. So you need 4 basic things. You need tools. You need your editors and your assembler. If you're really just concerned with the binary blob, those are the only 2 you need. Right? You need to make your assembly, and then you need to assemble it into the binary blob so you can run your shellcode. Now, depending on how you're doing your testing, you might need a linker if you want to, say, make an ELF file that you can actually execute instead of having a crutch program that will jump to your shellcode, or you have a handy old exploit that you can use it on. And then similarly, you only need a compiler if you're compiling test programs, or if you want to make code that links against libc or something like that. So I assume that all of you guys are good enough to find your own tools and whatever you prefer. But these last 3 bullets we'll go into a little bit. You need to know your architecture, you need to know the actual OS you're writing for, and more than likely, unless you're superhuman assembly binary reading ninja, you're going to need to do a lot of testing to figure out that everything works. All right. So Shellcode 101, architecture. So for the Intel architecture, this means knowing all your special purpose registers, EAX, EBX, ECX, and so on and so forth. You need to know the different addressing modes of these registers. So EAX is a 32-bit register, AX is the lower half of that, AL is the lower half of that, and the different ways that you can get to the data that you need to be modifying. Endianness, so we're talking 32-bit, little Indian. And then you need to know how the specific instructions that you're concerned with in your shellcode are actually going to work. So you don't need to download the 5-volume Intel architecture manual and memorize everything, but the instructions that pertain to the shellcode that you're writing, you need to have intimate knowledge of those, because you need to know what registers they're affecting and how, right? What are the semantics of what that instruction is going to do on the CPU? All right, so for the OS, you need to know how the OS works at a pretty low level, right? You don't need to know where the start button is. You need to know which bytes go in which registers to invoke certain action out of the OS. So since you're basically asking the OS to do actions on your behalf, you need to know how to ask what. So different OSs document the formula for asking these questions, and some do it better than others. So we're talking about a calling convention. Basically, this boils down to a stack versus a register calling convention, but there's different hybrids and there's different kind of weird oddities that you have to keep in mind, something like Linux sockets. So here's a huge generalization. We're going to take our system call that we want to perform, we're going to put it in the EAX register, and then you have to pass the arguments to your function. Think of it like a function, so you have to pass your arguments to the system call. These are either going to go in other registers other than EAX, or you're going to push them all on the runtime stack. And then something like the Linux sockets, where you end up at the hybrid, where the Linux uses a register call method, but the socket information is pushed on the stack. There's only so many registers, right? So you can't push everything, or can't put everything in a register. And somehow you have to actually, you finish formulating your question, you actually have to ask the OS to perform the action that you want. And this is going to be done in 3 ways, with a software interrupt, a sysenter or sysexit combination, or what's known as a FAR call. And then, kind of by convention, it's just understood that at the end, the return value from your syscall is going to end up in EAX. But there's also some oddities you have to remember with that. All right, and the third piece that you need, or the fourth piece, the third one that we're talking about, is the test platform. Ideally, this code is somewhat OS dependent, so all the shell code that we're writing is very dependent on our architecture and our OS, but the test platform can be pretty generic, because we'll just compile it on whatever target we have. Since the shell code that we're generating is usually what you're going to run immediately after an exploit, our test platform is basically going to be the world's most vulnerable code. All right, and by this I'm not talking about some hugely popular mainstream OS that somebody would call the world's most vulnerable code. We're talking about an application that basically all it does is a jump to the code that you want to run. And then for network testing, basically we want to accept an incoming connection and then immediately transfer control. So there's many variations of this on the web. A lot of them just deal with local shellcode testing. They don't lend themselves to socket-based testing. But here are the ones that I'm using. That actually shows up bigger than I thought it would. So just really briefly, We just create a big buffer, we create a pointer to that buffer, we read that from a file that is an argument to this application that's compiled, and then down here at the bottom we just jump to that buffer. So the idea is that we're going to run our executable as a single argument to that is our binary blob with our shellcode, and then we just jump right to our shellcode, right, so we can test it. All right. The socket or the network-based version of that is very similar. If you look in the lower right-hand here, this stuff is all pretty much exactly the same. We still have a big buffer, we still create a pointer to it, and then we set up a socket ahead of time. So these things, like the port number you're looking for, those become important for your testing, but you can change them whatever you want. You just have to know what they are. So we set up a socket, and then again, basically we're just doing our jump to the shellcode. So we set up an existing socket so that we can do things like find sock. Okay, assembly versus shellcode. Every shellcode payload has a distinct goal. It can't be non-deterministic, right? You can have, the idea is once it's become interactive, the shellcode's probably done. The goals that we're talking about here are pretty finite, pretty small goals. Something like open an interactive shell, that's where the term comes from. Add a user to Etsy password, edit a file a particular way. These are all common payloads in things like the Metasploit framework. There's also some other kind of hidden desirable goals. One big one is the absence of nulls, right? Everybody knows why nulls aren't there, right? Why can't we have nulls in the shellcode? Store copy, right? Because C-style strings are terminated with nulls. I need to go back and look at the first presentation today because he showed some shellcode and there were 3 nulls for every byte, and I have no idea what that was being used for. Must not have been going through any C-style functions, string-style functions. Oh, okay. Hey, he's right here. No, I know. I should have been paying closer attention, I guess. That was too early. So anyway, absence of nulls, and then we have kind of a off-the-end kind of a goal of smallest size possible. So it depends on how you're getting your payload into the target, but the idea is that for generic purposes, you don't know how big the buffer is that your shellcode is going to be copied into. So the smaller your shellcode is, the wider range of targets it's going to work for, right? And we can get around these limitations with things like stage loaders and whatnot. But the idea is just to get it as small as possible because you don't know how big the buffer is. And then another common thing that a lot of people forget about, we have no file format. When we compile it, when we assemble this stuff, we end up with a binary blob. These are just the instructions that the CPU is going to be executing. So there's no like ELF header or anything wrapping around it. The ELF headers are designed for things like the OS loaders to know how to load all the information when you do it. Here we don't have a loader, right? We're just creating the actual binary. So getting the kernel to do stuff for you. So the kernel has predefined actions where you can ask the kernel to perform for you. How you formulate the question varies from system to system. These are normally called syscalls, and they have the 3 different ways we mentioned already: interrupt, farcall, and sysenter. So farcall. Most people regard far anything as a leftover from an antiquated segmented memory model that nobody uses anymore. Right? All of your popular OSs use what's called a flat model. So all of the virtual address space is addressable. The farcall not only specifies an offset in the memory, but it also specifies what's called a segment in the x86 architecture. And that segment, for purposes of this discussion, we can just think of that as some region of memory that's addressed in a different way. So we have this huge area of physical memory, and we can say there's a segment here, a segment here, and a segment here, and each of those have an offset 0. So they're not literal physical addresses, we've just named them in different ways. And we can also use those as permission-based things, right? We can not let certain subjects have access to different segments and so on and so forth. But anyway, all of these concepts relating to far jumps, far calls, far whatevers are pretty foreign to people. So for example, we can jump to offset 0 of segment 7. So we have our opcode for a far call, 9A. We have our offset, which is going to be relative to the segment base address coming from the GDT. And then we have our segment descriptor number. So this is going to be segment 7 in the GDT. So segments in general relate to regions of memory, but they don't have to. There's plenty of other types. So some have special types, like a call gate. So in a call gate, when we go to that portion of the GDT, an offset doesn't make sense because it's not a region of memory. This is going to be a method to get from ring whatever to ring 0, or to a higher privilege level, lower numbered ring. So this is a very common way to get from something like ring 3 to ring 0, right? And just like the flat model, all contemporary OSs really just use 2 rings, right? Ring 3 and ring 0, and that's where you see these in all the presentations in the papers. All right, so the neat thing about call gates, everybody has them, or something similar. You need some method to get from ring 3 to ring 0, right? So we can get in discussions about IDTs and interrupt vectors and that kind of stuff too, but everybody has something similar to this. All right, the unfortunate or the sucky thing about syscalls is there's a lot of nulls in them, right? So by definition, you're probably going to have a pretty low segment selector. Nobody uses a segmented architecture, so there's no reason to have a full table of them. So there's very low numbers of descriptors in the GDT. And then the offset for something like this is always going to be 0, because you're never jumping into the middle of a memory segment. This is just a gate to get to something else. So the offset's always going to be 0. So we have a bunch of nulls. And the nulls are not good for shellcode. So these are normally manufactured as part of your payload, as part of your shellcode. And you can do something like make your shellcode FFs and then knot them to have the processor turn all the ones to all zeros. And then you've kind of manufactured yourself nulls in that way. Unfortunately, creating this is very expensive. So ideally, you only do it once and then you save a pointer to it basically. And you can call your pointer repeatedly later. Even if you do that though, you still have all this wasted time that you have to use to generate this, this function, so to speak. And then there's this other method. Intel observed fairly early that syscalls happen a lot. So they made this fast system call instruction, sysenter paired with 6exit. Basically, it does the same thing. Intel claims it's a lot faster, and it has some caveats to it. You have to kind of set things up just right before you make the call. You need to put some stuff in EDX, put some stuff in ECX. Your function that you're manufacturing is basically going to end up looking like what you see down here. So similar to the FAR call, this is expensive to manufacture in your shellcode, right? You're wasting precious bytes in your shellcode setting something up. If we don't have to do that, it'd be much better. All right, and the final method, the third method, is with a software interrupt. So just like your keyboard and your mouse and all your other hardware that generate interrupts all the time, we can generate an interrupt in software with an instruction called int, e.g. int80. That's what a lot of OSs, or a lot of the Unix-based OSs use. So this will basically raise an interrupt to the CPU similar to a hardware interrupt, and that will be used as an index into a table called the IDT, an interrupt vector, and then that will then locate code that will execute and actually handle the syscall. So the int80 is just used by convention. It's really just an index into this table, so it can be whatever. So this is pretty much as good as the PowerPoint foo gets in this presentation. I don't have any cool pictures like the last guy. So we have this table. Interrupt software occurs. We see the int80 happening on the left-hand side. When the interrupt occurs, several things are going to happen automatically as a byproduct of the interrupt. The CPU is going to push a whole bunch of stuff on the SAC, among them CS, eFlags, EIP. If you haven't written interrupt ISRs, interrupt handlers, basically you save state when you go into the interrupt, and then you handle your interrupt and you muck with the registers as you're performing everything, and then you restore state right before you go back. Across a system call, most of that stuff comes back except for the return value from the system call. So normally in EAX, but as we'll see in a second, sometimes other registers have like different return values as well. So this 80 is an index into IDT. This blue box will say that the physical memory address here is the base of your IDT. There's certain predefined ones for things like divide by 0, special exceptions that the processor handles. So if you do a divide by 0, it'll index into here, and then you still have to handle that. It's just this vector is predefined, right? You still have to have it make your ISR that says page fault can be handled this way, or whatever. The rest of these are all user-defined, so they can have whatever meaning you want. So 80 indexes into somewhere, we get this descriptor. This descriptor has two portions for our purposes. One is, whoops, gotta watch that. One is an offset to a segment. So in a non-segmented model, this might be a linear offset. but it's still an offset to a segment. The other, a descriptor, so we can find the base of our segment, and then this other piece is an offset into that segment, which finds the code that actually handles the syscall. All right, so not super important to understand exactly where the arrows go or whatever, but interesting to know that interrupt comes in, finds a vector in the table, and the table tells you how to find the syscall handling code. So syscalls documentation is a little bit scattered. Again, if you're trying to play at home. Section 2 of man generally will provide some C-style prototypes and some information on what the return value from a function that looks like this in C would be, number of arguments, the types of arguments, and things like this. However, finding the actual number of the syscall, so not like the number of arguments, but saying that this is syscall 4, that doesn't show up in the man pages, so you have to go find that somewhere. So here's some common locations in Linux. It might be here, in Solaris, and syscalls.h, and so forth. It also might vary depending on your distribution. You might have to follow your dependency tree and find them in there somewhere. All right, another kind of neat thing, syscalls are pretty easy to observe. So take out your handy Linux box, open up an editor, and type in this stuff over here you see on the right. So we have a 32-bit assembly. We have a single section, a single global symbol. We push the byte 1, we pop it into EAX because we know that exit is system call 1. Gotta stop doing that. And then we XOR EBX. So this is not really required. This is going to be the value that exit is going to return. You know, exit 1, exit 0, exit 2, so forth. So it's not really returned if you don't. It's not really required if you don't care what the exit value is. And we'll see some more examples of that in a little bit. And then you raise your software interrupt. You do your interrupt 80, which invokes the kernel handler for the syscall. So we'll compile that. Notice here we're using ELF because we're just going to actually execute it. We're not going to use one of our vulnerable programs to as a wrapper around this. So we can make it ELF, we can link it, and then we can use a program called strace, right? Really big, red, bold, whatever. Strace your executable, and that will just show you all the system calls. So it loads it, it does the exec.ve to actually get it executing, and then after that you'll see all the system calls that your OS does, and if they chain down, if one system call handler actually calls other system calls, you'll see those as well, right? It's tracing all of them. So this XOR of EBX on Linux is going to be the argument that makes this be 0. So if you were to set EBX to 2, this would change to 2. Then you see the strace process detaching. So very easy to observe. All right, so our first Solarisism. If you say it really slow, if you're a Solaris guy, Solaris background, if you're just drunk, maybe strace sounds like truss, all right? Strace in Solaris is a totally different thing, all right? So you need to use truss to get the strace-like functionality in Solaris. The build tools also are a little weird. For example, GCC is not in your path by default, so you have to make sure to add some things to your path. The assembler, AS, in my testing, it links against libc. We all know that GCC links against libc, so that's why we're not compiling our shellcode with GCC. We're just assembling it directly. But anyway, it seems to me, not being a Solaris background guy, maybe there's better ways to do it, but it seems to me that it's just easier to make your payloads on some other box and then transfer them to Solaris for testing. Right? So use NASM and then SCP them over or whatever. No? All right, so these are not the man pages you're looking for. Every distribution is different. There's very little continuity from man pages from system to system. Generally, distributions kind of keep it the same, but they don't have to. So Solaris has different sections. To specify the section, you actually have to use the -S option on the command line to get to the different sections, and then there's also subsections, right? So 3C would be the C library in man section 3. This is useful because a lot of man pages you're looking for will at first appear to be non-existent because they're not where you think they might be. So you might need to get familiar with sections like 3socket and 3C to find what you're looking for. Widely useful is to know that man in Solaris has a -L option that will list all the sections of a string. So if you say man L socket, it will list wherever socket comes up in any man section. You can find the subsections that you're looking for. Okay, so versions of Solaris. I have no idea who's in charge of the versioning scheme, but so we have stable releases. Solaris 10 is what they're called. So it comes out in December of 05. January of 06, they decide to add grub. June of '06, they add ZFS and other things, right? That's not the only edition, but that's like kind of the main one as I scan through what they do. So they have all these releases that come out, and they kind of just name them after the date. So you could have Sun 10.6.06, and you could have Sun 10.11.06, and they're different. They're both Sun 10, but that's how they name their stable release, their editions. And then totally independent of that, you have development releases. They call this the Express Developer Edition. And from what I can tell, basically what happened is people wanted to try Solaris. They hear that Solaris is the next thing. The contractors like them, the government likes them, whatever. They want to learn Solaris. They download Solaris 10, and they don't have anything that they need. All the tools that they're familiar with, and nothing works the way they want to. So Sun makes this Development Edition. The Development Edition has all the stuff that you really want, right? It has the build tools built in and everything. So think of this as Red Hat Enterprise and Fedora or whatever. Two different trees. And then kind of independent of that, there's now also a project called Open Solaris. So Nevada, Solaris 10, Solaris Next, Open Solaris, they're all pretty much acronyms for the same thing. Developer Preview, they all have different distributions of Open Solaris. So all these different things going on. Found this slide somewhere buried in a Sun PowerPoint deck. And it kind of shows you the development cycle. A little weird, but basically for our purposes, we see features go into the development train. Sometimes they get bounced back out and they go into this Express Edition, so they can make people think that they're going to like buying Solaris 10, even though those features never actually end up in release. Again, Red Hat versus Fedora, right? But some features hit the development train, and they actually filter through and they make it into the stable release, right? So the idea is that the important one is this yellow arrow down here, where we have new things that come into Solaris 10 as opposed to just updates and bug fixes and stuff. Oops. All right. So like many OSs, Solaris claims to have some level of POSIX conformity. All right. I don't know what the last OS is that claims total conformity. But anyway, Sun's really nice. There's actually a man page that delineates out that this version of Sun OS does these things in a POSIX way, and this version of POSIX and everything is pretty nice. Most OSs have a very transparent layer. So POSIX gets translated down to the system call, and there's not much in that translation phase, right? It's kind of a pass-through layer. Check out the differences between C prototypes and in sections 2 and 3, and like how the calls actually work. There's very little translation that has to happen there in most OSs. So Solaris is taking advantage of this abstraction layer, and they're saying we'll provide you this API to the higher level, and we will then actually perform the actions however we want down at the lower layers and accomplish the same goal. So for example, Solaris didn't used to provide an interrupt for performing syscalls. So shellcode and everything else is formed to use sysenter exit or the farcall method. So you have to do one of these constructive methods. So now it's relatively undocumented, but there's an interrupt 91. So it's not in 80, but it's the same thing, right? It's just an interrupt that's a vector into the IDT. The calling convention smells a lot like BSD. So you push your arguments on a stack, you put your system call number in EAX, and then you raise your software interrupt. Note sometimes additional things come back in something other than EAX. So if you're looking for register state to be preserved across system call, that might not actually happen. So you just have to be cognizant of that in your testing. All right, so the original Solaris 10 release used the farcall method. Later S10 updates includes this int stuff. So I don't know exactly where that happened. Digging through all of this is not my idea of fun. Plus you can't find some of these older releases. You go to the website, you have to log in and register before you can download it anyway. If somebody wants to actually donate me all of these exact versions that have ever come out of S10, maybe someday I'll get to it, but still not a very interesting. But anyway, sometime in the updates, this int91 became available. It's defined in sys.h, and for Intel, you dig down into trap.h and you see that t-syscall_int is pound defined to hex 91. So there's different libc libraries. There's a libc.a for sysenter, a 1.a, a 2.a for syscall, and a 3.a for the interrupt. They all work, right? They're just different methods. If you dive down into the source code for Open Solaris, syscall.asm shows that the int and the farcall methods are actually almost one and the same. They just basically handle subtle differences in the semantics of what that instruction does for the CPU. So like, what exactly was pushed? Did E flags get pushed automatically, or do I have to do that manually so that I can match it and I can have a stack frame that's the same for both, right? So it just kind of handles the idiosyncrasies. Whereas sysenter is kind of a different beast. It has a different basic block in the code, and it has to do things like set up the EAX and the ECX. The EDX has to have return IP, some of those, so we have to watch what goes in there and how they're used. All right, so here's some example. The old way. So we set up a FAR call. We have this strange hex value that we put into EAX. Again, the idea is that these nulls, we can't put those in there because we can't guarantee that we're not going to go through a C-style string copy. So we need to push this other string and then do something like not. So all of a sudden, this string becomes this in EAX, right? We can push it. Now ESP is pointing to this. We can clear EAX. We can move a 9A into EAX. We push that. Now all of a sudden, on the stack, we have manufactured our FAR call. Right? So we have our 9A, we have our offset, looks like this in assembly, FAR call, and then we have a ret sitting there at the end. Right? So we've kind of manufactured a function that will do this FAR call for us. So now we've done that once, so if we want to make multiple syscalls, we want to save that so we don't have to manufacture it again. So we'll move ESP into some register that we're not going to use later on. So we're going to store it in EVP in this example. And now we can actually do what we want. So now we've done all the manufacturing process. Now we can clear EAX. We can increment it because we're going to demonstrate an exit. We can push the 0. Again, if you don't care what the value is, you don't have to push it. And then you do a call EBP, which basically goes up here and does the FAR call and invokes the system call for you. All right, so here's the old way. All right, new way looks like this. And it's new for Solaris, right? So now we're going to clear EAX, we're going to increment it, we push it onto the stack, and then we push this dummy value, which is kind of odd. If you guys have done FreeBSD stuff, it might not be too odd to you, too foreign. And then we do our software interrupt. So we can see all of the overhead that can be saved. Right? We, instead of generating this thing, we can now just use the software interrupt to do it for us. Good, the blue shows up pretty good. So just really quick about this dummy value. Solaris and FreeBSD, they basically expect that you're calling a function to invoke the kernel for you. So in assembly, it would look something like this, where you, to do your system call, you would push your arguments, you would move your system call number, and then you do a call kernel. Right? So this is going to be your kernel call function, and you could add extra stuff in here if you needed to do extra stuff when you call the kernel, but then that's just going to do it for you. So when you make this call, you're going to push the EIP onto the stack, so we need to emulate that by having these dummy values here. Also kind of interesting because we can use these dummy values sort of like free pushes for the next system call, as long as we are careful about how we use the stack. All right, more Solarisisms. The sequence of system call for popular shellcode, widely known, right? Bindsock has been around, bindshell has been around for a long time. Various different, slightly different names, but they all have the word bind in them, right? And the word shell in them. So we're going to do a socket, we're going to do a bind, a listen, an accept, and then a dupe2 to duplicate our file descriptors, the standard in, standard out onto our socket. And then we're going to exec VE, and that's what we're going to exec VE bin sh or whatever. So the kind of interesting one that's highlighted there is dupe2 because it's a little different in Solaris. So unfortunately, even though it exists in section 3, subsection 3C in man, it turns out that there's not actually a system call for dupe2. Right? It just doesn't exist. There is no dupe2. So this is another example of an abstraction layer. So we can call dupe2 in the function, and then when it gets compiled and assembled down, it gets translated into different system calls that accomplish the same functionality. So for shellcode purposes, this is just annoying. We have to go now figure out how dupe2 is emulated or converted in the Solaris world. So we have to work around this. So in Solaris, it's achieved through fcntl. We have a descriptor, a command, and then a variable argument and a C prototype for this. So basically, command you can think of as a subcall. So dupe2 is going to be subcall number 9. So what we're used to seeing as dupe2 old new is going to look something more like fcntl old new old 9 and then new. Right? We're just using a subcall to this. So this actually isn't going to add much to our shellcode complexity, but it still has to be handled. Otherwise, we're not going to get our file descriptors duplicated, and our shell is going to be interactive on the target, not interactive remotely, which is what we really want. All right, another Solarisism, extra arguments. So we're used to seeing very specific things. So in BSD, for example, we see the socket requires three things, a domain, a type, and a protocol. Solaris SoSocket requires those things, and in addition, it has this fourth value that one can only guess what it's used for. We can see an indication later on in a slide coming up. And then we get this other thing called SOV, socket version. So, but as long as the shellcode works, do we really care what these values are for? Not really, right, as long as it works. Essentially, this is going to amount to extra pushes because we need to make sure that we have the right number of arguments so that our system call actually completes. All right, so what is SOV? It's defined in socket var. It could be one of these 5 values. So quick glance, we can see that SOV default, stream, and the BSD, quite likely we're going to be able to use any value between 1 and 3. All right, just looking at the naming and going from the source. But it turns out through, so in theory, 1 through 3 to work, but in practice, pretty much any value is going to work. All right, so this might require some testing, and at least in the first case, we might want to be cognizant of this. Okay, so how many arguments are there? We can go to sysent.c, and it'll tell you. There's the last thing, the rightmost thing is the number of arguments. So socket has 5, bind has 4. Basically, socket has 2 extra arguments, and all the other ones that we're interested in, bind, listen, accept, connect, they'll have 1 extra argument. So digging through these related C files, we can see the prototype for SoSocket. We have family, type, protocol, and dev path and version, so device path or something. But we also see that there's another path that we can take for a different prototype, and that 4th thing can be null. All right, that's much better for us. As long as we can force it down that path and have a null argument, then we don't even care what dev path is. We don't have to research it and whatever. We can still end up with a good, successful socket call. All right, so the basic formula. Figure out the syscall numbers from the name to system file. Figure out the number of required arguments from sysent.c. Make some assumptions about SOV, maybe, if you want to play by the rules. If you just want working shellcode, you probably don't really have to worry about that. Find the counterparts for the missing syscalls, like dupe2. Use BSD-style shellcode construction, so args to the stack, syscall and EX, do our software interrupt. And then while we're doing all of that, we're just going to kind of watch our registers and make sure that registers that we're trying to preserve across system call actually are preserving their state. Okay, so let's do a quick demo. So we're going to view compile a vulnerable program, view assemble and link some shellcode, and we're going to note the size. And then we're going to test it using netcat and our test program. Right? The source for these are going to just be on the slides. So if you download the slides after the conference, you'll just see them there. All right. So yeah, I am using Vista. People have been attacking that all day, but Vista is my host, and we're going to actually use Fedora to make our Solaris shellcode. So it's a very diverse OS set that we have up on the podium today. All right. So here we are in Fedora SC6. And we're going to look at some shellcode. So let's look at 43. So look at the next slide. All right. So this is basically going to be bind sock. Can you guys see that okay? The blue might not work, but that's okay. I'm going to annotate the blue. You can see the other stuff, right? So we have bits 32. We're going to be 32-bit code. We're forcing it to assemble a 32-bit. Again, we have our obligatory section and our single global symbol start. We're going to clear out EDI. We're going to multiply EDI, which is going to clear out EAX and EDX as well. We're going to move our syscall number into the lower part of EAX. We're going to push byte 1, which is going to get a single 1 on the stack. But for free, when we pop that back off, it's going to clear EBX and put exactly the value 1 into EBX. We're going to start pushing our arguments to the call. So we'll push the zeros for that question mark, for that 4th argument that we don't care about. And we're kind of doing something a little dangerous here. For this call, for the very first call, we're not going to actually push the value for SOV. So depending on very specific circumstances, you might actually want to push that, because now we're depending upon a value that's outside of our stack frame. Right? This is something that we didn't actually push that is going to be going in as SOV to our first system call. So you might want to put this byte back in there. So we push empty for our questionable, our null that we need in our fourth argument. We push empty again for the IP. We increment EBX to 2 because it was prior 1. So we push our socket stream, we push our PFINet, and we push our dummy return value in EDI, so we have that return sitting there on the stack, so that when we do our software interrupt, it goes to the right place. It expects that return for that kernel call to be there. So we can kind of actually use this as the next push, as the first push for our next system call, as long as we're careful about how we maintain the stack. So at this point, we should have successfully done our SO socket call, and we should get a good socket return back from this. All right. So socket actually alters EDX, in case you're wondering. So we're going to push EAX, and we're going to pop it out into ECX. Because we did one push and one pop, our stack is still in the same state, so we can still use EDI as our first push to the next call. Then we're going to do a sysbind. So we move the number for sysbind. We push this odd-looking string here, which is going to be basically our sock adder instruct, which needs to be null terminated. So that's why we pushed EDI in our prior call as our dummy return value. So now we move ESP, that's on our sock adder sits on the stack. So we move our stack pointer into ESI. Now ESI is a pointer to our sock adder structure. We push byte 16, which is going to be the length argument to our next call. We push the pointer to the sock adder. We push the socket, which is ECX, which if you remember, we saved that from our socket call. So now we've correctly set up all the arguments on the stack for our bind call, and we need to push again the dummy value before our system call or our software interrupt. So at this point, we should have successfully done a bind. Now we can do a listen. Interesting thing about listen requires a socket as the first argument, and so did bind. So it's actually already sitting there on the stack in the right place. So as long as we don't muck with the stack, when we do our listen, we don't have to set up any of the arguments. We just have to put the right value in the EAX. So all of these things are here because conceptually, if you were just doing this from scratch, this is probably how you would go about doing it. But if we're cognizant about what the stack actually looks like, we don't have to. We can just do our system call, and the socket is already there, and the backlog we don't really care about. It can be any value as long as it's greater than 1, I think. Right? So as long as whatever's there is greater than 1, which is going to be our pointer to our sock adder instruct, if it's a pointer, it's got to be greater than 1, so we can use that as our backlog. So we'll have a huge backlog, which you don't normally see in programming, but it still works. So our next call will be accept. We push our, okay, this is kind of weird because again, stuff is sitting on the stack. But for here, we're using our dummy value is going to be our call for the FCNTL to do our dupe2 for the next loop. So we're pushing as the dummy value, a value that we're going to use later on, so we're not wasting that those bytes in the payload, in the shellcode. Then we do our dupe2 loop. This is a very common loop in all shellcode. This is basically going to do a little bit of a dance where you push some stuff on the stack and you pop it back off so that you can maintain counter state across calls. And the kind of subtle oddity is that we have this subcall thing going on where we're actually calling SCNTL instead of dupe2. So that's where you get the big difference. But basically we're decrementing EVX as we go through here to duplicate file descriptors 2 and 1 and 0 onto our socket, so that our file descriptors end up going remotely across our socket, and when we type stuff into our exec-VEing program, that environment has been copied across, so when we type stuff, stuff typed remotely goes to our bin shell, and the bin shell output can come back to our remote client, right? So we can actually interact with the shell, the interactive part of the shell. And then we do our exec-VE. Again, this is very common code. We null terminate our bin shell string or whatever shell you're trying to execute. You say a pointer to that and so forth. And you move your exec-VE, and as arguments you get a pointer to the string, and then you get the argv, and then your NP, and your environment can be null in this case. And we execute it and we get our shell working. So that's the only one I'm going to go through because you can kind of see the thought process and how bind shell works. And you can work through the slides on your own and get through the thought process and how the other examples work. All right, so let's remove the slide 43 binary. All right, so I'll do a NASM using NASM assembler. binary format. So on a previous slide, we specified ELF there because we were going to execute it natively. We just wanted to do a /a.out and have our shellcode run. In this case, we want actual shellcode so that we can see the size. So we don't want to link it. We don't want to wrap the ELF header around it or anything. We just want the actual binary blob. So we'll specify NASM to assemble it as binary. All right, so we get a word, D-word error. That's on that long string that's specifying the sock adder. So don't worry about that. So we'll look at the size. Slide 43. All right, so we can see that the size is 84 bytes, which is pretty respectable for a shellcode that's not staged or anything. So we'll come back to this size later. So now let's go over to Solaris. And we can see over here we have a couple of things. We have our vulnerable programs that we saw earlier. So if I look at these, oops, no vim in Solaris. All right, if we look at these, you can see that they are in fact just the same thing that are on the slide. We create a buffer, we read argv, and then we transfer control to our buffer here. All right, so if I look at the word count on the payloads that are already over here on the Solaris box, we can see that we have these sizes. So the size is increments. So this one is going to be our bind shell, this one is going to be callback, and this one is going to be findsock for the different slides that are coming up here. Thanks. All right, so anyway, basically we're going to run our vulnerable program, and as our single argument, we're going to use the shellcode. So we're going to do a bindsock in this case. The 8813 translates to port 5000 in the human readable port way. So at this point, our vulnerable program is running. It's gone through and it's copied stuff into that buffer, and it immediately started executing our shellcode. So some of the system calls have already happened, and it's basically waiting in its listening state at this point. So our highly vulnerable program, let's see here, can I save some typing? Yes, I can save some typing. So I do some netcat to my Solaris box, and I specify the port that was pre-known in my bind shell. And like so many security examples, it was very boring and it's not very flashy, right? So at that point, we have exploited our highly vulnerable program, and we are now connected to our shellcode. So we could do things like ID, you can see root, you can uname, and see that we're actually on a Solaris box. We know that that window was a Fedora VM. So we're actually on there. We can cancel out and we can see that it stops. We can actually use truss. Have a sock adder reuse issue. Let me just jump to the next one. We can do it again with our callback code, just to demonstrate and show that it works. So now we'll use netcat as a listener. Right, so we'll set up the listen on 5000, so now it's 5000 on the Fedora box. Now you've executed now the vulnerable program is the exploit, and when it transfers to the payload, it does the callback code, and now the connection kind of went the other direction, right? So now I have an ID that just kind of magically appeared over on my listening netcat over here, and I don't know, it's hard to demonstrate that this stuff actually is doing what I'm saying it's doing, right? So I can do a cat etsy release and see that we're on Solaris or something. I don't know, kind of hand wave and hope that it's working. So anyway, we can terminate that. Here we can, since I don't have a reuse issue, I can actually use truss to show you the syscalls, right? So truss / vulnerable program slide 44. All right, so let me scroll back up. Or should I scroll down? Where's the stuff? All right, right up here. Right here we can see that we're doing an SO socket. We have our inode, our socket stream. We have our null value that we don't really know what it does. We have our SOV default. So in this particular example, I'm kind of playing by the rules, and we're passing valid values here. So we have SOV default. We see our dupe2 stuff going on. We have our bind shell, so forth. If we look at a different one, like the bind shell, we can see here, not there, you can see here that in this particular payload, I'm not particularly worried about maintaining the SOV area, whether it's 1 or 2 or 3 or whatever. So I set up my socket, and you can see that my SOV value is this crazy weird number. This is whatever was outside of my stack frame. This is whatever was sitting on the stack when my shellcode started executing. So we might really be worried about that. But regardless, when we get further down here, you can see that bind's SOV is this huge negative number. So I mean, it literally doesn't seem to matter what that socket version is. This one is going to be some byproduct from my previous pushes, where it's interpreting a pointer or something. So we can see those work, and then somehow accidentally, oh, I know what that is. This is my listen, my client. So this is sitting in the register when I push this thing, right? It's still sitting on the stack, so I get that. So we get that, and then, oops. And just for completeness, we can actually use the network version to do slide 45, and we can do our find sock code. So this is where I specify my client port, and when I go there, then it's going to go through all of the possible connected file descriptors for where my socket came from and find it. So you can see it kind of rolls through, and it finds out that it was socket descriptor 5 or 6 or so, whatever, some low one, and it connects. So the find sock does that. All right, so all the code actually works. The int90 is working just fine, and this is on. Oops. Where can I see that? Probably in Etsy release. So this is on Solaris 10, and this is the 8.7. So sometime prior to that, the software interrupt stuff started working. All right, so come back to this. All right, so we noted the size, right? They're fairly low. Here's our bind shell, here's our callback, here's our find sock. All right, so now do a metasploit size comparison. So this int software method is at least 10% smaller in these 3 cases. I didn't go through and do the add user to Etsy password case or whatever, right? But these are the 3 main types of widely used shellcode, the bind sock, the find sock, and the callback. So we can see that we get at least 10% improvement on this. All right, so some other tidbits. Here's where you can find some information on, again, how to play at home. When you're searching through source for this stuff, sometimes it's easier to download it and use your own searching instead of using whatever's built into Solaris. So you can check out Open Solaris via SVN. It's about 1.5 gigs, but then you can use your own finds and fgreps and locates and whatever else to find the source that you're looking for. All right, and there's some more references. So other than that, open to questions. Is that a hand? Yes. You're right in front of a light, so I can't really see you.
Did you have any problems with different CPUs? So we did this, we ended up having it work on some computers, not other computers, CPU differences.
Because of CPU differences?
Having to put what CPU capabilities you're trying.
To tell you the truth, I kind of noticed that this worked and kind of ran with it. So where's the testing occurred? With my testing, I've tested in different versions of VMware. So I've tried it in a server. That computer that I have is probably server 1.0.3 VMware Workstation, what we're using here. I've tested it in QEMU, and I've tested it on a Dell 8400, and that's the only bare hardware I've tested on. So is that what you were asking?
I've done this on older computers and it does not work.
What's that?
Older Intel, this will not work. You will have to go back to your L call.
Older Intels, this does not work.
Yeah, your int91 will not.
That I won't totally discount that, but that doesn't really make sense. That question almost doesn't parse, because where the int91 comes from is in the source. It has nothing to do with the CPU. So as long as it's a CPU that has GDTs and IDTs and has this segmented model, which it has to for this other types of shellcode to work because of the way you're manufacturing the FAR call for the other shellcode, you'd have to be doing some weird compilation that says, if this old CPU, then don't compile this method of libc, which would be a pretty weird thing to do. But yeah, so yeah, it's all weird. So, but we all know Solaris stuff's kind of weird anyway, so I don't know. They might do that. Anybody else? Is that Dave that was talking? Yeah. Yeah, okay. All right, well, thanks for coming out. Okay, so the first thing if you want to learn shellcode, don't buy any assembly books. Because all the assembly books are like, okay, you're programming in DOS, so when you do this stuff in assembly, you have this DOS environment, and you can make these assumptions, which you don't have. Right? So no assembly books at all, honest to God. There is a book out there called Shellcoder's Handbook.